coming in the future. So at the moment what you know is as well we have the Xeons and we have the Xeon Phi, the multi-core and the many-core systems. And all of them support different programming standards, different APIs. The Xeons, they're growing. So far the Broadwell was, or the Haswell was up to 18 cores. Now with Broadwell we're joining a couple of more cores, and if you've seen before, what Jordi was talking about, cores are going to grow more and more, and we have more and more parallelism in the nodes, in the cores, on chip, and for example with KNL within one processor as well. So you will have different NUMA modes, you will have different options to play around with that. And basically also starting with the Xeon Phi, the Knight's Corners, that had up to 61 cores so far. Parallelism is going to be more and more important, and you not only need to be able to run in parallel, to scale parallel, but also to feed the data to all of the CPUs, all of the vector processing units, and to be able to not just turn from a compute-bound to a memory-bound code, for example, that you have computing power, but you cannot use it because you need to serve all of the data that you need to run. One of the things with the Xeon Phi Knight's Corner is also that its instruction set is a bit different from the rest. And with Knight's Landing, which is coming up now, everything will be a bit more integrated. You have binary backwards compatibility, and it's going to be easier. Also, the difference, obviously, between a Xeon system and an accelerator is that you have limited amount of memory. And all of this is going to be addressed as well with the newer versions, so that you actually have a host processor that you can use if you want to. One of the biggest important things is obviously the instruction set. The vector registers, they went from 256 to 512. So Knight's Corner, the Xeon Phis are the first products that have the 512 instruction set wideness, so you can use longer, you can use more data at once in one operation, and you can use more operands, for example. Obviously, this is also important to be able to feed all of these registers, especially with Knight's Corner, because it's an order execution core and it can't really take well issues of too much latency. Talking a bit about the architecture, what we're focusing on in general in servers is the two-socket Xeon system, connected by an interlink, quick path interconnect normally. And so far what has been used is Haswell, and now the new Broadwell Xeons are coming out. Skylake is out as a desktop processor at the moment and will be coming as a server processor within the next year or so. And only then integrating all of the different features for a larger professional server system for HPC systems. In general, what we're looking at with new processors is more and more hardware, more and more architectural benefits that we can use, and that we can make our codes use of to actually enhance and parallelize and run quicker. So we have a lot of ALUs that do lots and lots of operations. What is very important about the new ones is the vector ALUs, and also all of these numbers of performance and speed up are making use of the fused multiple add instruction. So basically you're having one instruction doing multiplication and addition, and this is what is going to give you a lot of power and performance if you can use these instructions. Because instead of doing a couple of different steps, you're just doing it with the FMA steps, integrating 3 operands in one operation, and ideally working on vectors as well. So with this kind of operation, you can, instead of, for example, in a Haswell, you have double the amount of flops compared to the pre-standard Sandy Bridge, and with a new Xeon Phi Knight's Corner as well as Knight's Landing, you get even more performance out of that. You can see that depending on the vector length, you have different amount of flops that you can do per cycle. And obviously more vectors, more data means more operations, more processing. So you're quite enhanced there. So instead of using the traditional multiplication and addition operations, using the fused multiple add, you can do all of this, these operations, ax squared plus bx plus c, for example, as this polynomial evaluation. Instead of 16 cycle latencies and 2 cycles of throughput, you can do all of this in 10 cycles of latency and 1 cycle of throughput. So this is very interesting if you have actually access to newer hardware, if you have access to these kind of resources. You can just recompile if your application is already prepared for this kind of vector data, if the data is nicely arranged and nicely aligned. And then you can just, by a simple recompile, make use of the additional instructions. And in general, especially the Intel compilers are quite clever, and they also tell you if they were able to use advanced instruction sets or not. And you can also see and learn how to understand why not. Obviously, with each generation of processors, there's more and more improvement. There's quicker chips, there's less latency, there's more bandwidth. I have a lot of slides that I will just skip through or just show quickly, because you can then later on look at them for your reference. But I'm going to explain a bit more of the different things and touch different systems and ideas, so that's why I'm going to give you a broader overview. Skylake as well. We're going to have more instructions that are being executed quicker. We have a bit of better things about the caches. But what Intel is focusing at the moment is what you can buy now and what is also available now, which is the newest processors of the Broadwell family, which is the next upgrade from the Haswell that a lot of systems have, or even the more previous Sandy Bridge. So as you can see, the parallelism grows. We have, instead of 18 cores, we have up to 22 cores. Instead of 36 threads, we have up to 44 threads, and there's also more caches. There's 10 megabits more of last level cache, and it's all basically growing in numbers of processors, of cores, of hyper-threading cores, and so on. Like Jody said earlier, you will have more and more parallelism everywhere, and you need to take care of that. One of the biggest improvements with the new Broadwell is actually the memory speed, that it went up from up to 2,400 megahertz. Which actually gives you also a huge boost if you need to transfer a lot of data, if you need to move a lot of data around towards your memory. And this is one of the things that is interesting with Xeons, but also with Xeon Phis even more so, that you will have problems moving all of the data to your cores and managing all of this performance. Obviously, Intel wants you to update to the newer system, so the new chip on the same kind of same kind of benchmarks is quite quicker than the previous Haswell machine. And looking at real-world applications, it also gives you a boost in just changing the chip and using a new instruction set and being able to run more load at the same within a quicker time. Also, obviously, they're targeting different markets, so financial services, life science, and geoscience are quite explicit applications that are being used a lot, that are being optimized a lot, and that lots and lots of people are actually using their systems for. Apart from more cores and more threads, there's also less latency in the memory and more bandwidth, so you can transfer more data quicker and you can process data quicker. One of the more interesting things as well, if you have heard about all this already, is that the CPUs nowadays, they change the clock frequencies. And before, with older generations, all of the different ALUs, all of the different instruction registers, they change to the same kind of clock frequency. So if for some thermal reasons the core had to be powered down a bit, the AVX instructions as well as the scalar instructions, so both vector as well as scalar ALUs, had to scale down to the same frequency base. Whereas now with the newer cores, there's less of a models for this. So for example, if you are using very heavily the vector instructions, the AVX instruction set, it might be that the processor slows down for this from 2.2 to 2 gigahertz or something like that. But on the other hand, the scalar instructions, they're going to keep on the same power or on the same clock speed as before. Therefore, not slowing down your serial or your scalar part of the code, even though you're making heavy use of the other instruction registers. So this is getting everything a bit more dynamic and makes it more complicated to get some proper performance idea, performance numbers, because apart from scaling up and down the frequency, if you're not pinning your executions to a specific core or to a specific thread, then everything is being moved around as well. So these chips, they have a lot of intelligence to run in an optimal setup. If you're working in a data center, then it's important, depending on the cooling, depending on where in the rack the CPU sits, or the node, how much temperature it gets and how it slows down or not. It's also one of the things you can configure to be active or not, to have the difference of the turbo boost, but it depends a lot on your specific situation. For the Xeon Phi coprocessor architecture, so far what is available is the Knight's Corner architecture as a specific extension card that goes into a PCI Express bus. And in the future, now with the KNL systems, what is going to be available is a socketed processor that goes directly into the mainboard, as well as the extension cards via PCI Express. So this gives us some specific differences in how to program it and how the applications can be optimized on these kind of architectures. And also for next year, or maybe later, there's the next generation Knights Hill planned. We saw before in the presentation from Jordi as well that the Knights Landing, they're going to have 3+ teraflops dual precision peak performance, more than 6 teraflops in single precision, and you're going to have 72 cores now. So up from 61 to 72 cores. The older Knights Corner product, which is available at the moment, is GDDR5 memory. That's the same kind of memory that's been used on graphics cards. It's very quick, it's very low latency, but it is limited to up to 16 gigabytes only. So depending on the application, obviously you might have some issues fitting everything into that. You might have some issues moving lots of data around because you're going via the PCI Express bus. So the Knights Landing addresses this by having some high-speed MCD RAM, which is on package, available from 8 to 16 gigabytes. And this comes in a couple of different models that you're going to be using, which I'm going to be explaining later. But also, most importantly, it has access to the full system memory and up to 786 gigabytes DDR4 memory of the host. In addition to that, the Knights Landing is going to be introducing a synergy between the Knights Corner and the Xeon instruction sets, so it's also supporting AVX512, and it is backwards binary compatible with AVX2 and earlier instruction sets. So whatever you have on a Sandy Bridge or on a Haswell, you can take the binary, you can take the library, and you can run the same stuff on the Knights Landing. Obviously, it's not going to run with the same performance because it's a tiny bit of a different hardware, it's a tiny bit of a different architecture. So for best performance, you want to recompile the applications to make use of the new instruction sets and of all of the features that are available. And as we also saw, Intel OmniPath is very much upcoming now, and this is also the fabric that is being used to connect the Knights Corner CPUs and chips. And you're even going to get an option to buy a chip that has a fabric connection on the die, on the chip itself. So you don't have to go via external buses. So far, the available Xeon Phis are there in 3 different families. We have the 7, the 5, and the 3, depending and aimed on different markets, on different use cases. And they're all available as an extra card in a dense form factor, with active cooling, with no cooling, depending on the use case that you're having. Also interesting, if you're interested, there is some special offers with the Intel Parallel Studios. So you can actually get a card and you can get a license for the compilers and the whole development set from Intel, which is actually quite nice. And I'm going to give you a short overview later as well. And at the moment there's an open beta program for the new tools. So everything that I'm going to show you is available for testing until October this year. And you actually get free support via Intel Premium support as well. And people are invited to try everything out and give feedback because it's quite nice tools, they're quite powerful, and Intel is always happy to hear about your experiences. So, explaining a bit, the current Xeon Phi Knights Corner architecture is only available as a slot-in card, as I said before, and it communicates with the host CPUs via PCI Express bus. So that means just like in a GPU situation, if you need to work on the accelerator, you need to transfer binaries as well as data from the host to the accelerator and back. For this kind of work, the Xeon Phi is actually a bit easier than CUDA because first of all you can just program as you're used to in C and C++, whatever language you want to. You can compile, you cross-compile for the architecture. With the Intel compilers, for the Knights Corner are the only ones supporting it so far as I know. But for Knights Landing, GCC and other free compilers support all of the instruction sets, and you can compile for that without an issue. The extension card itself runs a BusyBox Linux, so you can log in, you have a shell, you have all of the tools that you need if you install them or if you compile them specifically for the mic system. It's relatively easy with Intel compilers. It's ICC, your normal compiling flags, and at the end -m mic for the mic architecture. So you can just have standard libraries, for example, that are dependencies on some of your applications. You just recompile them for the Xeon Phi, you copy everything over, or you do it directly on the Xeon Phi, and then you can build your applications and run them natively. You also have the options of running something on the host and using offload mode to the card, or running something on the card and doing a reverse offloading. There's lots of different combinations. It also depends on how your cards are connected, what kind of network connection you have, how you want to ideally work with the accelerators. As I said, it's limited everything by the PCI Express bus, so you have a relatively slow link there for large amounts of data. Obviously, if you can just access directly the main memory, that would be better, because then you don't have that kind of bottleneck. So far, with Intel Knights Corner, you can have up to 8 co-processors per host. So 1 teraflop each of these cards, more or less in double precision. If you're doing the diffuse multiplets, you can have 8 teraflops just from the accelerators, plus whatever is your host. With the KNL, I assume it's going to be the same. You can have the bootable system, plus additional sockets with extra cards. So this obviously depends on your application, what exactly you need to do, if you can use all of these cores, all of this power. And to run on the Knights Corner, you have the Intel Many-Core software stack, which needs to be installed, which gives you a couple of things, of tools to manage the installation of the system. In the Knights Corner, one of the biggest issues with the data and moving of data and instructions around is that everything is a ring bus, and all of the cores need to communicate via this bus. The Knights Landing architecture, as I will show you in a couple of slides, has a different interconnect, which is way quicker and which does not have all of these latency issues. You have L2 caches directly on each core, and these are fully cache coherent in the full system. You have a bidirectional ring connecting all of the cores with the memory and the instruction sets caches. You have DDR5 memory using 8 memory controllers, and you have a maximum theoretical bandwidth of 352 gigabytes, which is being quite okay, but obviously if you have only 16 gigabytes as maximum, you're limited by this as well. The next generation Knights Landing, on the other hand, as I said, is directly connected, if you want, to the base board, to the main board. It's going to be available in, I think, 3 different editions. If you are making use of the double precision fused multiplet, you can get more than 3 teraflops out of 1 card. With single precision, more than 6. So depending on the application, you can get a lot of power in one single workstation on one server node. And it's the same thermal footprint, one of those, as a 2 Xeon system. So that's why also comparisons are normally done between double socket Xeon and the Xeon Phi or Knights Corner, to see exactly what the same kind of power input gives me in return of performance per watt or performance per time or whatever your measure might be, but to keep it in a comparable level. It's going to be, or it is supporting the Intel AVX 512 instruction set. The advanced vector extensions 512 is a big set of instruction set that come with different specific instructions that are being supported most by Knights Landing. I think there's one TSX instruction which only will come with the Xeons from Skylake. The rest of it, everything that is supported by Knights Landing, is also supported by Knights Corner. So, and with the addition of the AVX 2 instructions from the Xeons. So all of this fuses, and in the future you're going to have only, hopefully only one big set of instructions for all of the different processors available from Intel. I said before, it's 72 cores now in the Knights Landing. You have 4 threads per core. These are out of order cores now, so they can better hide the latencies of memory transfers and all of these. You have GADA and SCADA support now in hardware. Before it was either fully software or software and a bit of hardware assisted. You have some advanced branch prediction, so you get less penalties for issues like this if you're not, if your loops are not well aligned. And you have a high cache bandwidth. It's based on older Atom cores, which is Intel processors that have been used in netbooks and ultrabooks some time ago. It's a Silvermont generation. and they put a couple of enhancements specifically for HPC, and obviously learning from the issues that we had with the Knight's Corners and that people are encountering of the different programming issues. One of the most important and interesting things is that you have NUMA support, and you can actually divide this guy into different NUMA nodes. I'm going to quickly go over that in a bit as well. And you have different modus of how to use the high bandwidth MCD MRAM. And as I said, exactly, as a standalone bootable processor and also as a PCI Express card. So if you have a system now with Xeon Phis, with Knight's Corners, you can just replace the Knight's Corners by Knight's Landing by getting the slotted version. Or if you just have a system that you want to try out something without getting a new main board and new everything, you can just buy an extension card and start playing around as well. So the Knight's Landing, in opposition to the Knight's Corner, instead of a bidirectional ring, has a 2D mesh. So you have the tiles that are all interconnected, and you have the memory controllers in this picture here and here, there and there. All of these tiles, each tile contains two vector processing units with the shared L2 cache. It's the same again, it's a fully cache coherent system. And the interesting thing is that you have now have the two vector units, so you also need to see how to share instruction between these ones. The system itself, as you have the different memory controllers, as I said before, you can select different NUMA modes with that. And you can even split it up in a way that, for example, you make a cross in here, you have 4 different sectors, and you have all of the tiles with the cores that have the memory in these controllers all close there, so they can access it quickly. Otherwise, depending on how your data locality is, how you place your threads, you might not want to have information requested from this core, which resides in that memory, so it has to traverse in a way or the other through the whole core, or the other way around. If you're having things up here and they need to communicate with stuff down there, or the parts of the L2 cache here needs to access things there, you incur a bit of penalties for moving too much data around and not talking with neighboring cells. So this is all a programming challenge, a configuration challenge, as well as then at runtime you can do pinning and you can do different tricks to have your processes exactly where you want and your data where you want. Also, with the increased high bandwidth memory, it's another abstraction layer. So you have high bandwidth MCD RAM, you have the system memory, the DDR4 RAM, and you have the caches of the actual cores. So that's a pretty picture of a die, and inside we have all of the core architecture as I started to explain before. We have our vector ALUs, and down here we have a legacy bit. This is for the scalar and the backwards compatibility. So if you're using some older instruction sets like ABX2 for example, instead of using the whole 2 vector units and all of the possible instructions, you're being confined to this one. So obviously it makes sense if you have access to a newer system, recompile your code, recompile your applications and libraries and make use of the new instructions. If you're having some older legacy libraries that are only available in a closed format for example, or already compiled, with the new KNL, at least it's binary compatible, so you can use these parts that you don't have any influence on and just use them within your whole tool chain without any issues. The onboard high bandwidth memory is not a high latency memory, it's not a low latency memory, but it's a high bandwidth memory. So it's a tiny bit slower than the DDR memory from the previous generations. But if we're reading a lot and if we're reading for a long time, we have a higher bandwidth and we can transfer more data. There's 3 different models to use that. It's a cache model the first, the flat model, and the hybrid model. So what does this give us? We have the CPU here, the socket of the KNL, and our cores have their last level or L2 cache. And if they need to get some data that is not in their L2 cache, they can first ask the high-speed on-chip memory, which is within the same socket contained. Or if not, if the data is not in the MCD RAM, it's going to ask via the system bus, via the PCB, it's going to ask the main memory of the system. So if we have applications that rely a lot on data, that are being read and wrote a lot, we're going to want to place them close to the CPU into the MCD RAM. You can do this by programming your application in a way, or in the easiest way, in the cache model, you just let the operating system use this additional memory, up to 60 gigabytes, as a transparent cache. So you don't need to change anything with your application, and you can actually reap the benefits directly. It's not as effective and not as performant, obviously, as manually managing it, but it gives you a very good speed up for basically doing nothing yourself. And in addition, if your application and its data all fits within the 16 gigabytes, or depending which size you have, then it gives you a very high speed up by just placing your whole application in the quick MCD RAM. In flat models, you manually manage which parts of that memory are being allocated. You can specifically place elements in there. You can say, for example, using the memkind API that has been developed, you can, for example, say only allocate data more than 1 gigabyte, up to 4 gigabyte, or up to 16 gigabyte. You can set limits. Place this exactly here in the quick memory, and everything else, other variables that I declare, things like that, can be done in the main memory of the host system. The hybrid model gives you the option of switching, mixing all of these. So you can use some part of the high-speed memory being used as a cache from the operating system, and the rest being used in your own application. The good thing about this as well, if you use it manually or in a hybrid model, is the DDR RAM and the MCD RAM is the same physical address space, so you don't even have to move things around too much or have to rewrite addresses with that. You can just address it like normal. The different modes are being chosen at boot time, so this is a configuration that needs to be done by the sysadmins or the support staff in the centers where you work. And depending on the application and depending on your workload, one or the other works better. If you have the time to optimize, the flat model where you have full manual control is the best, obviously. But if you just want to quickly get some benefits, you can try the cache model and see if this already helps you a lot. As I said before, it's low latency, but not lower than DDR. So DDR is a bit faster in latency, but it has a lower bandwidth limit. And MCD RAM, especially when transporting a bit more data, you can do it for longer and for quicker. And so, as always, try to load larger chunks. Don't do small operations, because then you get a big overhead, obviously. If you need to address different cells all the time, it's going to be quicker with DDR memory. But if you have your code nicely aligned, your data vectorized, and all of your instructions as well, and you can just read in big chunks, MCD RAM is going to help you a lot. Specific where you place your application and data for the KNL, as I said before, does your application, for example, fit already in the high-speed memory or not? Which kind of the different modes are we going to use? Use the data that is really, or keep the data that is being used a lot, that is being worked on a lot in the high-speed MCD RAM, and consider the affinity of your processes and your threads depending on where you're running on. The three different options available: the KNL as a normal boot socketing chip, the so far as a nice corner availability as well, the card with the PCI Express bus, and you also have the KNL with integrated OmniPath. So you have direct fabric in the socket in the chip. The amount of PCI Express lanes obviously varies depending on the model that you're using, because the same pins are being used for other communications. These systems are available for pre-order at the moment as well. KNL systems are available. I'll give a link as well at the last page. But if you want to just have access to these kind of things, there's also some courses and webinars run by by Intel's partner Colfax at the moment, and they will give you access remotely via SSH on a system which at the moment has KNC, Knight's Corner cards, but in the future will be upgraded to Knight's Landing cards. So this will be one of the easiest ways of getting some access and playing around a bit, especially if you don't have an access in general to a Knight's Corner or an Intel Xeon Phi system in general. Performance, again, is compared one Knight's Landing card against the double socket Xeon system over here. Performance relative and performance per watt as well. And as you can see, these are benchmark numbers. But obviously the performance is getting better, and the performance per watt is obviously also way better if you're using the correct instruction sets than a multi-purpose Xeon. So in the last couple of slides, I'm going to go quickly over some vectorization ideas. You have I don't know how many of you are actually optimizing or developing code. Anybody played around with vectorizing already? Okay, a couple. So we have the difference in in task level, data level, and instruction level parallelism. It's different levels that we need to take care of. Intel provides compilers for the bottom stuff, so you don't have to think about that. And then there's programming models for parallel systems, and OpenAPI, for example, or MPI to harness parallel power without moving around too much. The main thing is to use single instruction multiple data, to use vectors, to work on a lot of items at the same point. So instead of adding x and 1, y and 2, z and 3, w and 4 to these, we just do it in one step using vectors. So if we place our data in here, in these boxes, we can use, instead of doing 4 additions at the same time, instead of doing 4 addition operations, we can do it with 1 addition operation at the same time, working on the whole vector. So that's the basic idea. You need to format your data, you need to format your code in a way that this is actually being possible. And if you're using the Intel compilers, they will help you a lot with this as well and tell you what is and what is not done. These vector instructions, they have been growing from generation to generation. So we started at some point with the Pentiums and the MMX. Then there came the different versions of streaming SIND extensions, SSE. The newer ones, AVX and AVX2, which are now 256 bits wide and which are being used in Haswell products at the moment. Then we have AVX 512, which has been first supported by the Intel Xeon Phi Knights Corner, which is 512 bits wide, so you can fit more and more operands in this vector. And you can do more, you can do work on more data at the same time. As I said, there's also a tiny bit of a difference between this is the instruction sets for the Xeon processors, and this is the instruction sets for the Xeon Phi processors, including Knights Landing. So there's a couple of instructions that are not being supported by all hardware, but in the future, all of this is going to be probably within one big Xeon, or whatever comes after the Knights Hill platform as well. So it's going to be easier for applications to be optimized for a multi-core platform, which can be a Xeon, which can be a Xeon Phi, which can be anything in between as well. The ideas are the same for all of these because you're having parallelism, you're having problems with memory bandwidth, memory bounds, and so if you optimize your code for Xeon, it will run better on Xeon Phi. If you optimize for Xeon Phi, it also should trickle back to Xeons. And if you use all of these kind of ideas in future generations of compilers, you will have it easier to get more optimized code. And in future hardware products, you also will be able to reap the benefits if you have your code prepared or if your instructions are well prepared. I already went over the difference in between the instruction sets. So basically, as you can see, if the number of instructions you need to do, if you're just working on using a scalar, using AVX2, or using the AVX 512 instruction sets, you see how it differs the amount of total number of instructions you need to do. For example, the loads, the hits and the misses. And scalar, they are very high, obviously, and if you can start loading data with 256 bits or even 512 bits, you have less and less instructions for that. If you do single precision adds, you do 1024 using the scalar instructions, 128 using AVX2, and because you can fit even double that into the AVX 512, you only go down to 64 instructions. So in total, it's a difference between 4096 instructions, 512, or 256 instructions. And this is basically where the performance comes from. If you're able to use these instructions, if the compiler is able to compile your code, your application, your library to make use of these advanced instructions, you get a lot of performance. You can use from the Intel compilers as well as the GCC compilers also supported AutoVectorisation, which gives you a bit of automatic vectorization, but normally does not work very well. I think I heard something like 10% or so of the code can be optimized with this, but it's so-so. Then you have guided vectorization and low-level vectorization. You also have, ideally, you use code that somebody else wrote. You use libraries that are already prepared. So we have the Intel Integrated Performance Primitives, IPP, the Math Kernel Library, which is very well known as well, which is a highly optimized library in assembler for lots and lots of scientific software and lots of optimizations of applications being commonly used. And now it's available for free as well for everybody. And then there's also data analytics for big data and these kind of things. It's a new product that they're also trying to get more and more people on board because it really helps you optimize your data operations and your system. Then there's also an interdistribution for Python, which is new and which you can try out, which is in beta. It's nice. It has NumPy, SciPy, and all of this linked together with Intel MKL. So you're getting the speed up and the optimizations of MKL. You're getting threading in Python for free, and you're getting other things. And you don't even need to do anything. You just need to switch your interpreter, and instead of your system Python, you're using the Intel Python distribution. And it also works with pip and Conda and other package managers, and available for all three important platforms. So that is also one of the things that Intel tries to get more and more into, and well, helps you to make more use of the hardware that you have by just providing you with the tools and making it relatively easy. As I said, the beta is open, so everything is available, everything is testable, you can play around, and the developers are very happy of getting some feedback. Obviously Python is also being used a lot in Spark, Hadoop, and all of these. So this is very, very interesting to try around with at least, and have a look how it goes. Then, coming back to the vectorization, you can use the different compiling switches. You can have vectorization normally with O2 anyways included. You have, as we saw with Jordi as well, you have different things that cannot be auto-vectorized, data dependencies, if it's not efficient, or if we have a loop structure that is not very supported. So this is one of the things that you can make use of, but it's not giving you too much performance. Here you can actually see the runtime using the auto-vectorization, depending on the different programs and different problems. So some of them actually give you less, where is it? 1, here's 1. So some of them, the auto-vectorization actually slows down the code a bit, because this is the compiler does not know exactly what it needs to do, and might do some things that hinder the performance. On the other hand, if your application is well suited, the compiler might just give you a very big boost by doing automatic things. But what is more interesting for the developer is actually the vectorization reports that come with the Intel compilers, which are very interesting, and you can give them in different levels of verboseness. So what they do is they tell you exactly at what source code file, which line number, what happens. The loop was vectorized, for example, or the loop was not vectorized because a vectorization dependence has been detected, and this one prevents vectorization. The newer Intel compiler 17, they're giving you even more information. They're talking about a specific variable or a specific array size or part that is preventing vectorization due to data dependencies and other things. So we invite you to play around a lot with this, and as we can see, we have information about different phases of the compilation. So we have vec as a vectorization phase, but you can also get information. How does the compiler actually transform your loops, your OpenMP, the offloading instructions that you use. You can also use a trace analyzer to collect MPI traces, or you can have all of the information, but this will really expand the output quite a lot. This is quite helpful to learning what is the compiler doing, why is it not working as expected, and what could I do, for example, to enhance my code. Then we can use obviously different compiler flags to influence the vectorization. We can use pragmas, just like OpenMP. Some of the Intel SIMD pragmas actually went into OpenMP standards later and got included there, so it's all relatively standard. Most importantly as well, which architecture are we compiling for? Are we compiling for the architecture of the system that we're running on now, which would be just the -X host? Are we compiling for Knight's Corner, Intel MIC, which would be -M MIC? And apart from that, you can enable and disable specific features, the different instruction sets, so you optimize your binaries for exactly the system that you're going to run it on, or that you're running on at the moment. Then there's also specific Intel compiler flags, depending if you're using the Intel compilers. As I said, for KNL, you can use a lot of free compilers, GCC, Clang, all of these will support, or do already support, vectorization, auto-vectorization, and the AVX512 instruction set. Just quickly a couple of basic steps, and then a couple of pictures about the software tools before I finish. So data layout, as I said before, is important how you have your data structured in memory. If you need to jump cells for each little element, x1, x0, y0, z0, x1, y1, z1, it takes more time to address exactly the cell where your data is, to load it, load first the first bit, then the next, and so on. So what you want is you want the data all nicely aligned in memory, so that if you read X, you read actually the whole chunk of X and you read it into a vector. You read Y into the next vector and Z into the next, or use Z as your output. So in this way, you can, instead of having several costly data accesses, you have just 1, 2, 3 strides, and you can put your data directly into your vector registers. There's also alignments from the different programming languages, different POSIX memory line options, but also the KNL Library, which is being developed by the Intel guys, gives you a high bandwidth mallocs to work specifically with the MCD RAM on the Knight's Landing, for example, which would be HBM malloc. Also for loops, it's important to vectorize. Ideally, we want to we need to split up loops into a peel, the main, and the remainder loop if the loop itself is not vectorizable. So we can then do some pre-processing, do some post-processing, but we vectorize the main body of the loop. And this is where we gain our performance. Obviously, depending what your instructions are, what you're doing, your remainder or your peel loop might be becoming your bottleneck then. So it works well for bigger loops and for lots of data transformation. If it's too small, the iteration numbers, obviously then you're having more overhead in managing all of this. And you can also always low level optimize, so you can use directly intrinsics and you can program for the hardware that you have. This is not very portable, unfortunately, but it gives you good performance. But this means that whenever you update your hardware, you need to revisit this, you need to revisit the intrinsics and write for a new instruction set. So it's not the best. So Intel offers you a couple of tools, now available for free for everybody to try. For example, the advisor, which gives you a bit of an analysis of what are you doing, what is your code doing, where can I perform better, how many threads are running. For example, here we have a CPU count depending on the scalability of the application. You get information of your source code as well as the assembly for it, and you get a lot of extra features. For example, you can see here, maybe if you can see, it says efficiency. There's a general gauge of how efficient the actual implementation of your code is at the moment, how you could maybe enhance it a bit, which instruction sets we're using, AVX in this case, for example, and what you can do to switch to or to transform your code to make better use of quicker instruction sets, of AVX 512, longer vectors, things like that. It comes with service, with trip count analysis and deeper analysis, so you can actually look which are the hotspots. It's giving you nice colors to see. Here you see, for example, efficiency and vectorization. It says 100%, so this is 100% effective for what the compiler and the analyzing tools think it has as a parallel efficiency. Here it says 60% or 90%, so you see also which are the ones that I need to concentrate on more, which are the ones that I need to focus on more, which are my hotspots, and where is already parallelism and vectorization more or less okay. Obviously you can filter, you can just look at the vectorized or non-vectorized loops. You can see how much overall time you're spending in there. Trip counts are already not mentioned. You see source and assembly, exactly. And you also have the recommendations. There's a little light bulb, and then it gives you recommendations, which is very, very helpful. It's within the IDE, and it tells you, oh, look at this. This is what you could do. This is the reason why your code didn't optimize, didn't vectorize. It gives you links to the internet, to forums, to these kind of things. So you can also, from within the IDE, start reading up and learning about how can I modify my code better, how can I program better to make use of the hardware. And most importantly, afterwards, you can actually verify that what you've been doing gives you an enhancement, gives you a speed up, less runtime, and so on. You can also work with OpenAPI. You see different worker threads. It works for Python, the new vTune as well. And as I said before, you have nice graphs, so red, yellow, and green, and it should obviously be more green than red. And the big red things is where you need to look and where you need to put some effort to optimize your code. And exactly. There's a couple of more detailed vTune analysis and how you look around. So you can have a look for basic hotspots, concurrencies, logs and waits, and advanced hotspots, general exploration, and also you have memory access patterns. So you can analyze how does your application access the memory, what kind of strides are being used, and then with look at KNL, you can start optimizing your application so that all of the memory intensive stuff goes into the high speed, high bandwidth memory, for example, and you can afterwards show that everything actually worked well. As I said, the beta, I think it's a cluster edition that contains everything that is in beta at the moment, but also Intel made available, especially the math kernel library and IPPs and the thread building blocks in academic or community libraries which are free, which everybody can use. So you can try that. In addition, the MKL, for example, you can compare with BLAS or OpenBLAS and see how much better it works for you. And if you want, you can just use the libraries provided by Intel free of charge and optimize and speed up your applications a bit. This is the link for the Parallel Studio Beta. This is obviously a bit newer than the 16. And it's in beta phase until October this year. You get access to all of the tools that you want if you select them. You have the Python, you have the VTune, you have the Advisor, and so on. And as I said, they also have support provided. One interesting thing as well is annotated source listings, so you can compile, and the compiler gives you some information on the specific source line, what is happening, what we could do, and then you can later go through that, generate text.pd, text.html, and it gives you a lot of opportunities to learn as well. And the optimization reports are even more advanced now, as I said. So basically, if you want to get ready for KNL and further instruction sets, you optimize your code now. There's also the Intel software development emulator, so you can actually start developing and testing chipsets that are, and instruction sets that are not yet available. And you can check all of that later. There's also, as I said before, you can pre-order the Xeon Phi systems from Coldflex. These are the guys also that are giving you access via webinar series directly to a system. There's more online resources with most important things. And what is also very, very good, the high-performance parallelism Perl books. Then there's the Intel Xeon Phi Night's Corner programming from James Reinders directly from Intel. And coming up this year in June or something, we'll have the Night's Landing edition available as well. And these books are very recommended in general for performance profiling, for parallel programming, and for using the latest Intel technologies. And so, yeah. Thank you.
We have time for one or two questions, fast questions if you want.
Otherwise, catch me later in the breaks.
Break or whatever. Well, thank you.